In the next couple of videos, we're going to look at some of the first examples where physicists trying to derive an expression to reproduce an experiment used what at the time was the only kind of physics there was, classical mechanics, and they failed to reproduce the experiment, and it was necessary for quantum theory to come in order to predict the correct result. So the first example we're going to look at is called Blackbody Radiation. So a black body is just some object like this box here, which when you heat it up, let's just say we're heating it up, starts to emit some radiation, and it absorbs radiation equally at all wavelengths, but it emits them with some type of spectrum. So this green stuff coming out here is radiation. I'm going to label this blue object as the black body. Black, of course, because something that absorbs radiation of all visible light colors is going to appear black. And then there's some type of detector, which we will not mention at all, which is going to record the spectrum of this radiation being output. Okay, so if we look at this spectrum, now try to get this color. If we look at this spectrum, then what we're going to be plotting is the density as a function of both the frequency and the temperature. So this is the intensity of the radiation that's going to be emitted by the black body versus the frequency of that radiation. Frequency nu, the Greek letter nu. And if you don't remember what the frequency is, just remember that frequency equals the speed of light over the wavelength. So wavelength and frequency are inversely related. And this, of course, is the spectrum. Okay, so if you use classical theory to try to derive an expression for what this spectrum should be, you'll get a result which is called the Rayleigh-Jeans law, just as a matter of trivia. It's not really important that it's called that, but in case you ever hear someone mention that, that's what it is, which is that the intensity of this radiation equals a constant, which is a product of several constants, 8 pi times the Boltzmann constant times the temperature divided by the speed of light cubed, and then this constant all times the frequency squared. So according to classical theory, the intensity of the radiation is proportional to the frequency squared. So at zero frequency we'd have 0, and then it's going to be a parabola going up from there. So if we just draw that there, let's try to do a little bit better job. Draw this dotted so that this is the classical theory. Okay, but it turns out that if you actually measure the spectrum, you don't get something which looks like this. You get something which looks much more like this. It goes up, it follows that parabola for a while, but then it tails off. It reaches some maximum and then goes back down to 0. Then, let's see here. Oops, nope, don't want to hit that. Okay. And some higher temperature, it'll be quadratic for longer and then tail off. And at even higher temperatures, even further. So this is T3, T2, and the orange is T1. And where increasing temperature, T3 is greater than T2 is greater than T1. You get a higher frequency for the maximum higher frequency for the max frequency as you increase the temperature. And this makes sense because if you can imagine something which might behave somewhat like a black body, metals, when you heat them up, they're first colorless because this emission is first in the infrared. It's at low frequency. Then you heat them up and they become red, which is at the low end of the visible spectrum. Then you keep heating them up and they eventually become blue, which is the highest frequency in the visible region, and then beyond that they become white, which is the peak is in the UV range, so pretty much all visible colors are being emitted equally. So in order to get a result like this, it took Max Planck in the year 1900 introducing a hypothesis that the energy of the particles inside of this black body, which are creating the radiation, which we now know are electrons, that the energy is quantized, that there are only certain allowed energies for the particles within this black body, and those levels are quantized such that the energy of a given particle is equal to an integer, n, times this constant h times the frequency. So the key thing here is that this constant n is an integer. This is the sign that n belongs to the group of integers, which is symbol, this double bar z here. So using this type of idea, Planck again derived this same expression, except what he got is that the intensity of this radiation should be, similarly, he got the 8 pi part, but then you have h over c cubed, and then this is times v cubed over the exponential of h times nu over Boltzmann constant times temperature, and then all of that minus 1. Let me draw a line here. This is getting kind of messy in there. Okay, so Planck gets this expression here, which is a cubic divided by an exponential minus 1. So if you look at that, you'll get a function which similarly goes up initially. If you do a Taylor series of this and you set h equal to 0, you'll notice that setting h equal to 0 will pretty much reproduce the classical curve. The Planck's equation will become the Rayleigh-Jeans law if h equals 0. But Planck noticed that if you varied this value of h, that he reproduced experiment whenever h has the value 6.626 times 10 to the minus 34th joule seconds. And that's what we know today as Planck's constant. And this is the first instant where Planck's constant appears, and it came because Planck had that hypothesis that the energy of the particles inside this black body were quantized according to this equation, E equals NHV. And that's really the point of this whole video, is that Planck had a hypothesis that there was some quantization of energy levels, and he got this constant here, which we're calling h, and Planck's constant falls out whenever you try to vary h to reproduce the spectrum of blackbody radiation. And at first physicists thought, well, this is kind of just an ad hoc idea that the energy of these particles inside of a black body have to be quantized. They didn't think there was much to this at first, but then we'll see in later videos Planck's constant is going to keep reappearing, and eventually Planck was validated by Einstein and then others that there really is quantization which occurs at very, very small scales. And this is just the first example of an instance where this idea was necessary to reproduce this physically observed spectrum, this blackbody radiation spectrum.